All right, let's take a look at the Unit 2 learning targets and get some extra practice with these. So, I don't know why this is checked. That's not even the right answer. All right, so the first learning target is, can you calculate sea level rise if you're given information about the volume of ice and the surface area of the water? So just as a little recap, we know volume of a rectangular prism is length times width times height, and area simplified is length times width. So maybe you would have centimeters cubed because you've got centimeters times centimeters times centimeters for an example. And then you've got centimeters times centimeters, so this would be centimeters squared. And then if you divide volume by area, you're doing length times width times height divided by length times width. So that cancels, you're left with height. You've got centimeters cubed divided by centimeters squared. So that cancels out, this cancels out, you're just left with centimeters, which makes sense because that's the unit for a height. So here's our problem. It says the surface area of the oceans is 3.619 times 10 to the 14th meters squared. If you have a glacier with an estimated shape of a rectangular prism with the following dimensions, and it completely melts into the ocean, how much sea level rise would it contribute in meters? So here we've got a length times a width times a height. This will give us the volume. So I can type into OneNote, my volume is 2.9 times 10 to the 8th times 4.8 times 10 to the 3rd times 26 equals 3.6 times 10 to the 13, that's meters to the 3rd. Then I have to do volume divided by area. So I'm going to take my volume, 3.6 times 10 to the 13th, divided by my area, 3.619 times 10 to the 14th, and that comes out to be 0.0995, but these all have 2 significant digits, so my answer needs 2 significant digits. So the answer would be 0.10 meters. Learning target 2, I can record a measurement with the correct number of significant digits. So let's look here. We've got 15, 16, 17, 18, 19, 20. We are going by the ones place. So we want to estimate out one more. So maybe 17.2 milliliters. See what our options are here. Yes, 17.2. And no more and no less. Okay, Unit 2, Learning Target 3. I can apply rules about significant digits to calculation problems and correctly record my answers. Which of the following is the correct answer for 0.98 divided by 1.08? So I would want to round to 2 significant digits. This one has 2, this one has 3. So my answer can only have 2. So it should be 0.91 grams per milliliter. All right, learning target 4, I can use dimensional analysis to convert units. What if I need to convert kilometers squared into inches squared? 1 kilometer is 1,000 meters, and 1 meter is 39.37 inches. So first I would want to write out what I know, not 1 over what I know. See, this one had 1 over the 2.2. That's not right. I want to get kilometers into meters, and it's 1 kilometer equals 1,000 meters, not the other way around. Not 1,000 kilometers is 1 meter, so that's not right. Okay, I want kilometers on the bottom because I want those to cancel out. And then I want meters into inches squared, so it's this one. This one's not right because look, it has kilometers and then kilometers on the top here. So you'd end up with some weird units of like kilometers to the fourth, inches squared over meters to the fourth, which doesn't make any sense. Here, kilometers squared cancels out with 2 kilometers. 2 meters cancels out 2 meters, and I'm left with inches times inches, which would be inches squared, which is exactly what the question's asking me for. All right, using the graphs below, what is the density of fresh water? Well, it's equal to the slope, so it would be 0.9813. So it's not going to be one of these two answers. And then here it says, what's the density of a piece of metal? Okay, blah, blah, blah. So mass divided by volume is density. That's 14.58 divided by 5.4. So I'm going to type this in just to be thorough, even though I can kind of see already what the answer is because it's the bigger number on top. So this will be 2.7 grams per milliliter. Okay. Unit 2, learning target 6. Use the image below. Object A has a mass of 12, an initial temperature of 40. Object B has a mass of 36, and an initial temperature of 0. What will happen when the two objects come in contact with each other, and what will the final temperature of both objects be? Okay, well, the ratio of 12 to 36 is the same as 1 to 3. So that means the change in temperature will be the opposite. So this is A, this is B, this is A, this is B. So the change in temperature, it's 40 total divided by 4. A will be 3 times as much as B. The total will be 40. So 3x plus 1x, I'm getting that from here. 3x plus 1x, that's 4x equals 40. Divide by 4, divide by 4, x equals 10. 3 times 10 is 30. That means A will change by 30 degrees. So it'll go down to 10. And B will go up by a factor of 10 or up 10 degrees. So the thermal equilibrium temperature will be 10. So I can eliminate this first one because it says the final will be 30 degrees Celsius. That's not right. This one says it'll be 10. This one says it'll be 10. So I know it's not this one because this one says 30. And let's see which one makes sense. The particles of object A are moving slower. That's not true. It's the hot one. It says it starts at 40. So that's not right. The particles of object A are moving faster. They collide with the slower moving particles of object B, making object B's particles speed up while object A's particles slow down. The final temperature of both will be 10 degrees Celsius. Yes, because A is the hotter one. So those particles are colliding with B. Once these two come in contact, they'll speed up B's particles, but B has a lot more and they're slower moving, so they're going to slow down that of A to a dramatic effect, 3 times more. Number 7, specific heat. Let's check this out. You're heating metal A, which has a really low specific heat, and you're heating metal B, which has a higher specific heat. If you have the same amount of mass of each, and you give them both 1,000 joules, which one will have a smaller change in temperature? Metal B, because it takes more energy to change the same amount by 1 degree Celsius. So you're going to see a smaller change. So metal B, because it has a high specific heat, which means the same amount of energy won't cause as much change in the temperature. All right, can you apply the heat of fusion? So the heat of fusion says it takes 80 calories to melt 1 gram of ice. So how much energy would it take to melt 1.2 times 10 to the 5th? So it takes 80 calories to melt 1 gram, and we want to melt 1.2 times 10 to the 5th grams. So I'll type this in one note, 1.2 e to the 5 times 80, 9.6 times 10 to the 6th calories. Let's see, because grams cancels out, so it's just calories. There we go.